So thanks everyone for coming. We're going to show you today really cool research we did in our company. We are from CyberX, a cyber industrial company. And I'm David, and this is Gosha.
Hi.
Yeah, great. So I'm the VP Research of CyberX. I've been in the IDF CERT. I've been doing there a lot of malware research and reverse engineering. Gosha, give a few words about you.
My name is George. I also served in the IDF, in the Intelligence Corps, and I'm a security researcher at CyberX.
And another guy who is not here, his name is Tal. He was part of the research. He's our machine learning researcher in CyberX, and he's doing a lot of work about modeling ICS behavior. So what we're going to talk about today, it's first we're going to take the view of an attacker and see how you can get inside OT networks. After that, we'll talk about the challenges of exfiltrating the data once you're there already. And we're going to show how we did it, our new way of doing it. So we're talking about OT networks, but we're not OT networks for for those who don't know what's OT networks. OT networks are operational networks, sometimes called SCADA networks. It's basically networks inside like a factory or a power plant or anything that produces something. And they are usually consist of controllers and HMIs, which control the controllers. And these networks are really critical networks because if you harm them, you probably stop the process, you stop the producing of a factory or producing of electricity, like we've seen that happened before in recent, it's not recent attacks, but in previous attacks, it happened before. So if an attacker wants to get inside an OT network, first of all, that's like, it's like really general way to describe OT network and IT network. But usually if they will be connected, they'll be connected using a one-way diode, something that passes only stuff from the OT network to the IT network. It's usually done because, think about it, you're monitoring some process in your operational network, producing some product, and you want all the data to be available on your IT network to make reports and make like statistics or something. So it would probably be connected using one-way connection. And getting to OT networks, it's a challenge, but it's not impossible. And getting out of the OT networks, like getting the data out of the OT network, is also a challenge, but it's also not impossible. And once you're getting into an OT network, probably think about it, if you're getting into an IT network as an attacker, you'll probably have some generic stuff like some PCs, like Windows computers, Linux computers, and you already have probably most of the data to attack the network. But when we're talking about operational networks are very diverse. There are a lot of vendors, different devices. If you want to harm some device, you need to understand what's the significance of the device inside the network. That means if you are just, I don't know, harming the controller that controls the, I don't know, the work clock of the workers, it probably some way harm the factory, but it won't stop its production. So the first stage before even attacking, destroying OT networks, making some harm, you have to collect all the data about the network. You have to get all the devices that are there. You have to get the mapping of the network, which security products are there, because you don't want to get caught. You need to get the device type and the firmwares, because sometimes controllers will act differently. Even the same vendor have different types of the protocol for different versions of the controller. So, and the other things, you probably need the programs themselves, the ladder logic. Ladder logic is program that runs on the controller and controls its main logic, which is usually think about a controller as a smart electricity circuit, which receives input from one side, from sensors or something, and from the other side, it produces some commands to do something. For example, if we have an oven that cooks something, and we have a heat sensor, if it goes too much hot, it will probably say the oven stop producing heat. So all this logic that takes data from the sensor and says the oven stop producing heat is usually written in ladder logic. Also, you have to get the schematics and the designs of the factory to find which PLCs does what, because for example, in the attack in Ukraine last year, they found out there's a protection relay that once it detects that something goes wrong, he switches to a backup plan. And they knew exactly to execute a denial of service vulnerability on that device, because they knew its importance, they knew how it's important. And you need to get, of course, patterns of how the users are working and stuff like that. So what are the main attack vectors? Probably it will surprise you, because it seems like really simple attack vectors, but it's because the nature of OT networks, they're usually very outdated. Their firmware versions or their Windows versions are not patched. They're using Windows XP. We have seen Windows 2000 on some of our customers, and probably the old attacks are going to work. So first attack vector is a malicious USB. Once you get a malicious USB to OT network, you can infect the network. Stuff like autorun-inf, which is like basically autorun on the USB. It's enabled by default on Windows XP and probably work in most OT networks. LNK exploits, like used by Stuxnet, are still probably going to work on OT networks. Or stuff like DLL search order hijacking, which means that the software that OT vendors design, it's not designed with, sometimes it is, but it's usually not designed with security measurements inside. So stuff like hijacking the DLLs is going to work there. So that's first vector. Another vector would be some external engineering laptop. Engineers are the guys that are programming the controllers, that are writing the ladder logic, and programming the devices themselves. And sometimes they're using their IT laptops they bring from home. Sometimes these are external contractors that do programming for OT networks. And it's enough to get their laptop infected. You even can spear phish them and make sure they get the network into the OT. And of course, it will be, it's another attack vector that can infect the network. We have seen some engineers being infected. It's usually because besides doing their programming using these laptops, they're doing other activities on their laptops and getting a lot of malware. Okay, so another attack vector would be, okay, that's an interesting one. During, I think, the last year, we have seen the NotPetya malware, and it was distributed by a malicious update. Someone hacked the guys from AmiDoc, which is the financial software, and it was distributed with some malware with it. And also an attack vector into OT networks. Most of the vendors, OT vendors, don't sign their software. So yeah, NotPetya, that's example. Dragonfly, which is a group that attacks OT networks, did it before. They concealed an AVEX Trojan inside one of the OT software updates and pushed it and infected an OT network using it. And these are some of the vectors. There's like 3 vectors I described now. And the problem, think about it, it's a network that's not connected to the internet. You're getting in there, you're collecting all the reconnaissance data. How are you getting out of there? And probably you can wait for the laptop to come back, and if it's infected, talk with the malware there and just throw all the data there. Or you can wait for the same or another USB to connect back. But the problem with that, it's going to take a lot of time for it. It's going to expose your malware on the OT network for exposure of detection. And it's possible, but it just takes a lot of time. So we decided to research into that specific topic and found some really cool way. So Gosha is going to show you now. We lost something? What we lost? Okay. Yeah, it's okay. Go for it.
Can we get the presentation?
Probably my fault. Maybe the cable here is not connected well. Embarrassing. Yeah. Okay. Okay, great. Yeah, go for it.
Okay, so before going deep into our project, let's have a little introduction to ladder logic and PLCs. So PLCs are small embedded devices. Usually they have some microprocessor like a PowerPC or a MIPS, have some storage unit and a firmware that runs everything. And they'll usually have a bunch of inputs and outputs. And you can connect sensors and motors and other stuff to those inputs and outputs. And this way you can build some industrial process. Like for example, making sure the water in a tank is at a certain temperature, or controlling a production line. How do you tell the PLC what to do? There is a special programming language. This programming language was designed to program PLCs to program an industrial process. How does it look? Well, here you have a simple example of a very small program. And you have to imagine it's executed from left to right. Imagine there is a current going from the left side and executing everything in its way. In this example, it will first encounter a condition, check if the state is indeed 0. In case it is, it will execute the blocks. In case it's not, it will stop there. So it's equivalent to the code you can see underneath. A typical project will contain a bunch of those lines. And by the way, they're called rings. Okay, so in our research, we worked with a Siemens PLC. Though we could have chosen any model or vendor, Siemens is not special in any way in this regard. Siemens like organizing their ladder logic into blocks. So a PLC will contain several blocks, each block with some part of the code. There are several types of blocks. First, there are the organizational blocks. This is somehow like the global code. All the organizational blocks are executed all the time, one after another. Then there are the function blocks. Function blocks are just like same as functions. They're used to organize your code, to reuse the code, normal stuff. And then there are the data blocks. It's where you store your variables, and later you can access them from the organizational blocks. Great. Now, we mostly use organizational blocks in the research because they have this nice property that you can insert another organizational block to the PLC. And this organizational block will be executed in addition with the already existing organizational blocks on the PLC. So you sort of inject code, so the PLC will keep doing what it was doing and will perform your additional organizational block. Okay, why did we choose to do this with ladder logic? What's special about it? Well, several reasons. First of all, detection. Ladder logic is not being examined by antiviruses. Antiviruses focus on normal executables that run on normal operational systems. And ladder logic is code that is being uploaded to the PLC, and no one really checks it. So if you upload a malicious code, no one will know. Persistency, it's a nice way to survive reboots of the PLC. And recently there was some researches that showed you can do cool stuff except controlling industrial process with the PLC. Even some vendors, they expose more APIs to the ladder logic, and you can do some low-level stuff like creating sockets, sending raw data, which opens a whole new set of possibilities. Some similar research from the past, the Tempest paper published by the NSA, that showed how you can leak data with electromagnetic emission. And a very cool research called System Bus Radio that FM encoded Mary Had a Little Lamp with some C program. Okay, so our setup. We used SDR Play 2, which is the small box that connects to an antenna on the one side and to a PC on the other side. And it basically lets your PC access the antenna. Then a regular TV antenna, maybe you can even see it from here. And the Siemens S7 1200 PLC with the default configuration. And again, we could have used any other vendor. Okay, so a high-level overview of the scenario we're presenting. Assume you have some PLC in some air-gapped network. So someone injects ladder logic that collects some information he's interested in, stuff that David mentioned, like the ladder logics of other PLCs. And he collects this data, and now he wants to exfiltrate it. The network is air-gapped, so he uses our ladder logic to create low radio frequencies with the CPU of the PLC and exfiltrate this data. Okay, so to achieve that, we had to overcome some challenges. First, the frequency used the PLC. What do I mean? Every PC, every laptop in the room, it creates electromagnetic waves. So if I walk around with an antenna here, I'll see a bunch of waves. But the frequencies that are affected by the laptop, they may vary depending on the laptop type, on the CPU type. So the first challenge is to understand what frequencies are affected by your PLC. So to do that, we used Console SDR. What do we see here? This is the output of Console SDR. So the x-axis is the frequency, and the y-axis is the time. So basically, you can see what frequency was strong at what time. So the light lines represent frequency that were strong during the whole recording time. The black arrays represent frequencies that were not strong. So to understand what frequencies are used by our PLC, we basically had to build this setup, an antenna pointing to a PLC, and start browsing the electromagnetic spectrum with Console SDR, looking for some kind of pattern. Meanwhile, we were turning on and off the PLC, trying to see if this will affect, if we will see some kind of pattern appearing and disappearing. So after some time, it took us some time, but eventually we found that our PLC affects frequencies in the range of 320 kilohertz to 400 kilohertz. Great, so now we know what frequencies are affected by the PLC. Our next challenge is to create change. Because to actually encode data, you can't encode it in a constant line, obviously. You need to be able to control it. You need to be able to cause the PLC to affect different frequencies or create a stronger signal. You need to have some kind of change. And you need to have that change through the ladder logic. So to achieve that, we had the same setup. We had Console SDR on. This time we had it pointed at the relevant part of the spectrum. And now we started writing a bunch of different ladder logic programs, always looking at the screen, trying to see some kind of a pattern. So our first attempt was to perform some mathematical calculations. We were multiplying numbers, doing mods, some trigonometric functions. This had no effect. We kept seeing the same frequencies all the time. Our next attempt was connect an Ethernet cable to the PLC, and this showed a change, but this is obviously not good because it requires physical access, but we saw that a change is possible. Next, we tried sending traffic. We were sending packets, receiving packets, trying to see if this causes some kind of change, but this didn't work as well. What turned out to work is copying large buffers of memory. We wrote a ladder logic. Basically, the PLC gives you a memcopy-like API. So you can give it one buffer and a destination buffer, and it would copy the buffer. So we saw that when we did that, there was this very nice shift in the frequencies. So every time you see a shift, it's because we were copying a buffer for 1 second, let's say, and the frequencies created by the PLCs would move. Great. So now we know what frequencies are relevant, and we know how to create a change. And we create this change through the ladder logic. Okay, so next we want to write an actual ladder logic that will encode data and send it. So first we had to decide what's a 1 and what's a 0. It really doesn't matter. Then we needed to create some kind of synchronization pattern. This pattern will later help us synchronize to the clock of the PLC. Then we had to send the data. So this state machine represents our ladder logic. First it starts by initializing, then it sends the synchronizational sequence by sending a 1 and a 0 for like 10 seconds, and then it simply goes over the buffer it wants to send, extracts the relevant bit, and sends it. Let's dive a little bit deeper. So the most basic part is the send bit part. Assume you have some kind of parameter called bit, and in case you want to send a 1, we perform the memcopy trick we saw previously. This creates this pattern where the frequencies shift. If it's a 0, so we just prefer some calculations, doesn't matter what. And this just leaves the frequencies at their usual place. Great, so now we can use this basic pattern to send the sync frequency, the synchronization pattern. So we just send 1 and a 0 interchangeably for a certain amount of time, depending on the length of this sync pattern we want to create. To send an actual data bit, we simply extract the bit in the ladder logic, and again use our send bit block to send it. Cool, so now we have our ladder logic. Now let's talk about the receiving side. Now it's important to remember that this is a one-way transmission. So you have no way of telling the PLC, it's okay, I received the data, or retransmit it, I didn't understand you. It's just the PLC always sends, and so he thinks that someone will receive it. Okay. So first of all, this is again the output of console SDR, and you can see that the pattern created by the CPU is kind of repeated, and it's exactly the same. And it repeats itself at different frequencies. But some of those frequencies are noisy. There is this constant noise that is always disturbing you, or a background noise that's making it hard to understand. This might be caused by some device nearby or by another component on the PLC. And if you move the PLC to a different place, the noise might be different. So you want to pick a good, nice frequency to work with, something clean without noise. So to do that, we first think of this whole thing as an image. We forget it's a frequency. It's frequencies and time. We just think of it as an image. And then we use correlation. We take a simple basic block of a transition from a 0 to 1, and we correlate it to the image. Now, correlation will have this nice property that it will be stronger if the noise is weaker, if there is no noise. And it will be especially strong during a synchronization pattern, because a synchronization pattern controls has the most of those transitions from 0 to 1. Great. So now we can automatically detect the optimal frequency to work with. So now we have just one frequency, one pattern. Now, next, we want to take this pattern And again, think of it as an image. It's a two-dimensional image, and we want to transfer it into a one-dimensional array. Eventually, we will want to distinguish between dark areas and light areas. So we need only one half of it because it contains all the information. And then we just average all the rows, and we remain with one number per row. And this number is either small if it's a dark area or big if it's a light area. Now we're gonna do another correlation, this time with a perfect one-dimensional signal. This is the signal we would expect to see if there was no noise in the world. So this correlation will have two nice effects. First, it will help us detect the synchronization. So we will know we are working with the best frequency and everything is fine. Because in case it's just a data transmission, we won't see as many bumps. So the synchronization, the correlation will be lower. And then the other effect is that it will tell us what's the perfect shift to put this perfect mask on the actual signal. And we will know how is the clock of the PLC ticking. So we will be perfectly synchronized. We will know when a second in the PLC ends and the next second starts. Great. So now we're synchronized to the clock of the PLC. And what we do now is we simply receive the data. So now we just have to wait 1 second, receive all the image that we saw on this optimal frequency, and just to make the decision whether it's a light or a dark area. Great. Now some statistics. After finishing the projects, we started to play around, see how far can we get the signal to work. And actually with our simple antenna, we saw that it works in up to 1 meter. Obviously, we didn't choose the perfect antenna for this wavelengths. So this might actually even go further. Our bandwidth was 1 bit per second, but this could have been way faster. Again, using just a better algorithm, maybe encoding the data in some way, or a better antenna. You can imagine that in a real-life scenario, there might be some exfiltration techniques where you mount an antenna on a drone, or you use some portable antenna to get near the PLC. Great, now the demo.
So is the demo working? It's probably not. It never works when it's live. So can you check if it's working?
I can see that it's not working. We actually had some problem with the ground cable of the antenna, unfortunately. We didn't think it might be a problem, but we prepared a backup plan.
Yeah, we have a video. So if we can switch to the presentation. Oh, sorry. Second. Okay. Great. Just press the play.
Okay. Yeah, so here you can see the setup, the antenna on the one side, the PLC on the other side.
Let's go back a little bit. Yeah, so
this is obviously the antenna, a normal TV antenna. One computer is connected to it. And here is the air gap and the PLC. So the PLC will be executing our state machine that we saw previously. And yeah, let's start. Let's close up on the PLC. Yeah, so this is the ladder logic we talked about. This is the programming environment of the PLC. Now it's just an easy way to tell the PLC what to transmit at the moment. You can create an HTML page on the PLC, then connect to it. And this is basically happening on the PLC, right? It's a computer connected directly to a PLC. and we write this on the PLC. So PLC will be sending our company's name now. Now we disconnect from the PLC. It's connected only to the power supply. And you can see the antenna. Here is the console SDR output. So this is an actual transmission of data. You can see those shifts caused by the memcopy, and they encode some bits. And then you can see it coming on the other side.
So yeah, that's the demonstration. Thanks.
Okay. It's also notes.
Yeah, we have a few slides. So it's last slide. How do we detect it? I mean, we can start detecting the crazy EM transmissions over the devices in our factory. We can try shield everything with EM shielding, but we think the most practical way would be detect the programming of the PLC over the network. It means if you have some a product that continuously monitors the network and looks for stuff like if someone pushes new ladder logic to the PLC, which you didn't approve, or suspicious traffic from the PLC, because if the PLC is doing the reconnaissance and starts scanning stuff, suddenly you have a PLC in your network that's scanning. It's probably weird. And if you have, of course, new devices on the network that just connected to the network and started doing stuff, it will probably be suspicious. And we think that's the best way to detect such attack. So, questions? There should be a microphone passing here, so just raise your hand and you can ask a question.
Hello, congratulations, good presentation, no matter the live demo. Those devices should be EMC compliant, so electromagnetic compatibility, they should pass tests and everything. I don't know if this would affect in case it was a certified EMC device, perhaps this was a leaky device. Have you tried doing something with foil, aluminum foil around the device and detecting from the power lines or the data lines? That would be an alternative as well. The second is if you can program affect the operation of the device using the antenna setup. Thank you.
Okay, so the first answer, some devices should be shielded, but as you see, it's a regular device. We didn't change anything. We didn't disconnect any shield out of it. It's just the way it is. It's not shielded. And there are other vendors. We did the tests on this one, but there's supposed to be other vendors that's not shielding it because, you know, it's adds to the price and they sometimes prefer not to do it because sometimes the regulation doesn't enforce them to do it. So it's not always done. And no, we didn't try to prevent it using shielding. It wasn't the purpose of the research. And for your second question, we can't really say if it can be affected back. We didn't try it. I mean, I don't think I've read a research that can affect it to back there, but I don't know, that's interesting. That might be the next research. Any more questions? Yes.
Hi, thanks for the presentation. Just curious, did you run the program with a like a system running as well, and did it affect that? So if you run a PLC with a defined program, did it interact with the program and therefore the outcome?
Want to answer that?
Yeah, it's a good question. we had some code being executed in parallel. The code, for example, the code that was extracting the bit that wants to be sent, he was extracting it all over and over again, which is like a shift and a AND operation. Apart from that, it's a good idea. Maybe we can check with more code, but there was some code running on the PLC while we were transmitting.
What is meaning the patterns are big enough to show the difference between our patterns of transmission and the stuff that's running usually on the PLC. They are not writing for a second to some memory buffer. So, any more questions? Yes. Yeah, there are a lot of questions. Okay. Yeah.
I wanted to ask whether is there any power surge or power changes during the leak itself?
Did we test it? Power surges during the leak.
What is the power surge?
More power consumption.
No, we didn't test it.
It's interesting.
Yeah,
but
interesting question.
Usually there's the thing with PLCs, they are usually working. They're working all the time. They don't have modes such as. I'm talking about this specific PLC. Maybe others does have. They don't have modes that reduce, for example, the power of the CPU. The CPU is always processing code. Is always running. Is always doing calculations, and maybe the memory chip generates more power, but the CPU shouldn't generate anymore.
Did you check what's the impact on the CPU utilization, and was that detected when you were running these scenarios?
What do you mean CPU utilization?
So the PLC CPU utilization, like did you increase any of the?
The percent. Yeah, as I said before, it shouldn't change because the CPU runs all the time. It's always processing inside PLCs. They're always executing OB blocks, and when they are not executing OB blocks, they're executing something. So it's like we tried putting more calculations on the CPU. I mean, make the ladder logic calculate more, and we didn't see any change. So it usually should stay the same, either it's running ladder logic or not.
Hi, thank you for this presentation. Have you tried with others PLCs nearby? Because in industrial environments, normally there should be others. So just to check if it's more very theoretical one or very practical that can work because of the noise, for example. If there are others PLCs, will they make same noise on the same frequencies, or they will shift a little? Or it would be too much noise to detect this and perform this type of attack?
Okay, do you want to answer that?
Yeah, I can say that we had laptops nearby, and it's a good question. Basically, if the other PLC affects a different set of frequencies, it should still work because they won't interfere each other.
Yeah, if it's different frequencies, it shouldn't interfere, and we assume that we produce enough the pattern is unique enough and unified to disable other
you might be able
noises.
You might be able to overcome this algorithm-wise, so yeah.
So you caused the effect while doing the memcopy. Did you analyze any of the other instructions to see if it would cause disturbances on? So we saw disturbances on all the different harmonics. Were you able to cause a disturbance on different harmonics? I'm just thinking if that's possible, then all of a sudden you've got a way of encoding more data because you can start doing different interactions using different instructions, and therefore you've just increased your bandwidth by maybe 100 to 300%.
That's a great question.
Well, we did test a bunch of other opcodes. As I showed, we tried to do mathematical calculations, and like send in traffic, and this had no effect, or we didn't see the effect. We basically, once we saw something that works, we sort of went with it. It's a good idea, yeah. Obviously, if you can affect different frequencies, then you can transmit more data faster. And as I mentioned, again, transmitting it really fast was not our objective. I'm sure we can, like 1 bit per second was just convenient for us, you know. It can obviously work way faster.
I would like to add also that maybe we should say it again, but what's producing the EM, the electromagnetic effect, is it's because the CPU writes data to the memory chip, and once it passes on the bus, it transmits the EM frequency. So the instructions themselves has no effect because they're inside the PLC and they're just running there. They're calculating something, but once you're talking with another chip on the board of the PLC, the electricity that passes there produces the EM frequency. Okay.
You said that with your antenna you could read your data from 1 meter length. Do you have an idea how far you could still be able to be on read what you are emitting?
Sorry, I didn't understand your question. Can you repeat it, please?
You said that with the antennas that you used, you could read what you emit from 1 meter. Is it possible? Do you have an idea of how far you can be with a better antenna and be able to still read what you are emitting?
So we didn't test a better antenna. We know for sure it works very good with 1 meter. And if you see our antenna here, it's just something from the store, like the most regular antenna ever. So it's nothing, there's nothing here. It's just, you can take a coil and it will be the same as this antenna. So we didn't test it, but we assume that better antenna, better results. I mean, if you have like satellite dish, like 100 meters long, you'll probably detect also from kilometers, but you know, that depends on the antenna. We didn't do it. I think there's a question there. Yeah.
You mentioned in your presentation that OT networks are very often outdated, right? And we all know it. And basically, we always recommend, hey, you have to update the newest version. But often it's not possible because hardware is tied to software or any other reason. What would be the mitigation then? What would you say customers should do, basically, to protect the outdated software the best they can?
So outdated software, usually it's not even possible to update them. There are controllers that don't even have updates for the vulnerabilities. And we think the best way is monitoring, passive monitoring. These OT networks usually do critical infrastructures, critical processes, and you don't want to execute like tools or scan the networks because these PLCs are also like, they can crash from regular stuff. So we think the best way is passive monitoring, like a span port or something, monitor everything, see what changes, and alert if there's something wrong in the network. Does that answer the question? Great, thanks. Yes.
Thank you. If you say passive monitoring, that would mean that you have to understand all different protocols, say Modbus, CAN bus, all this stuff, 30 different function calls in Modbus, different ways of implementing this stuff because you have a whole bunch of different vendors doing the thing. And the critical thing is then, what does it mean, monitoring? You have to baseline the stuff. So you have to get an understanding who talks to whom, how often, what protocols, what time, what data transfer rates, what protocol function calls, and
Great.
the whole bunch
exactly
of that.
What we do.
So, and then the question is it then, and you can hardly build a policy handwritten and maintained to build up a policy-based monitoring. You have to do some artificial intelligence kind of to figure out what's normal, what not, and then running against this. So is that something where the industry and CyberX is already at that kind of maturity state?
So just to clarify, he's not working for us, if you wondered, but that's exactly what we do. My team is responsible for the protocols. We're doing the reverse engineering for the proprietary protocols. We're building the DPI engines, the deep packet inspection engines. We're building the parsers. Some protocols have RFCs and are documented online, but some of them don't, and that's what we do. We're reverse engineers. And yes, what a company does, it looks in the network, it baselines everything. We have algorithms to detect if something goes wrong. We're analyzing the behavior of your network, your standard behavior of the network, and if suddenly some new PLC starts scanning your network, we're going to alert and tell you, okay, the PLC is behaving not normally. Do you have something you want to add?
I can just add that you said that all the protocols are different, but there is a lot of similarity between them. Like they all have a start PLC, stop PLC command. So yeah. So even a simple baseline is possible. Yes.
And yeah, I feel safe to say that. Oh, you asked also about machine learning. Yeah, so one of the guys that did the research, his name is Tal. He's a machine learning researcher. He's doing his PhD in Israel. He is a PhD student, and he's building for us. He has also an army experience. He was from the intelligence unit, and he's building machine learning models for this kind of stuff, for the industrial protocols. He's designing models to detect anomalous behavior, and we have also cool features like we detect anomalous behavior on protocols without any prior knowledge about them. So yeah, it's really cool. Any more questions? Great, thank you very much.